There we go. All right. Well, good morning, everybody. Today we're going to continue basically the same theme for a little while, but what we're going to learn is different ways of saying the same thing from a notation standpoint, but also it makes conclusions a little bit easier. So we're going to do something, we're going to work with what are called valid versus invalid arguments. And I've already given you some hints of the types of things we want to do. Now, when we're doing an argument, it doesn't really matter the truth of the statement itself. It's, can I make a logical conclusion based on the statements? So it'd be kind of like saying, all right, Samuel can fly, therefore, well, it doesn't matter if you can fly or not. If I start with that premise, what conclusion can I make that is valid? So a lot of times we worry about the truth of the statement rather than the validity of the conclusion. Does everybody understand that? That's why I said yesterday, a lot of time when you're doing logic, you'll use gibberish statements. You use statements that doesn't even make any sense, just so I can say, if this is true, what conclusion automatically follows? Okay? So one of the notations we're going to start with is if, we're going to say it like this. Okay? Or I should say, I should write it like this. I'm not going to write this. P implies Q, comma, P, therefore Q. Now this looks kind of weird. So the first statement says P implies Q. That's my first premise. My second premise is P. So I'm saying P implies Q is true. And we have P. Therefore, we have Q. If we score more points, then we will win the game. We scored more points. Therefore, we won the game. Does that make sense to you at least? Yeah, that's pretty basic. This type of logic is called modus ponens. It's Latin, don't worry, but you'll see that term come up and you go, what does that mean? That means basically you have a conditional statement and you met the criteria for a conditional statement. It's pretty simple. So then we say things like, I like to use this one, okay? Everybody knows this. You guys all know this, right? All Lannisters pay their debts. Tyrion is a Lannister. Can you make a conclusion? Therefore, Tyrion pays his debts. Is this a correct conclusion? Yes. Does it matter if the first statement is actually true? No. We're starting with the first statement and we're accepting it. Is there a Lannister out there that doesn't pay his debts? Maybe, I don't know. But if we start with it, all Lannisters pay their debts. We're saying this is the truth. Tyrion is a Lannister, therefore we can make this conclusion. Okay, this is modus ponens. Real simple. Now, we talked about contrapositives last day. Okay, P implies Q, P therefore Q. Let's start with the exact same statement. P implies Q, not Q. Can we make a valid conclusion that is absolute? What do you think? Therefore what?
Not P.
Not P. This is called modus tollens. It's basically the contrapositive in action. If we score more points, then we will win the game. We did not win the game. Therefore, we did not score more points. That's an absolutely valid conclusion. Now, again, we usually use statements that make sense to us. If we score more points, then we win the game. Okay. If we wear blue, we will win the game. We wore blue, therefore, we won the game. Does it really matter if wearing blue causes us to win the game? No. We're saying if this conditional is true, and I meet the criteria, right, then I can follow through. So again, don't get bent on whether it's true or not, saying if this holds, is my conclusion valid? Now we tend to like to use true statements. Again, like I said last day, we often use gibberish, meaningless statements, just so we don't get caught up in that part of it. Now, if the sum of the digits of an integer, spelled correctly, is a multiple of 9, then 9 is a factor or divisor of the number. Okay? For 342, the digits add to 9. Therefore, this is modus ponens, exactly. Therefore, what? We'll use good English. Therefore, 342 if the sum of the digits of a number add up to a multiple of 9, then 9 is a factor. The number 342, the digits add up to exactly 9, therefore 9 is a factor, or you can say 342 is divisible by 9. Now, can you give me the modus tollens of this? If the sum of the digits of an integer is a multiple of 9, then 9 is a factor. That is true. And now I'm giving you 342, and you say, yep, 9 is a factor. What if I said, I'm thinking of a number, and 9 is not a factor? What could you conclude?
It's not divisible.
No, if 9 is not a factor, it's not, that's the same thing as saying it's not divisible by 9.
They just don't add to 9.
Then the sum of the digits wouldn't add to a multiple of 9. That would be the modus tollens. Oh, okay, it would be exactly that one. So the modus tollens, you don't actually express the contrapositive. You express the conditional. But then if the conclusion is not true, then that leads to the premise not being true. Again, this is, like I said last day, this is how a court of law works. I'm trying to show, given this evidence, the conclusion is you're guilty. That's what I'm trying to show. So what do we start by assuming? Not guilty, and show that it leads to a contradiction at some point. That is the whole point of this sort of argument. Let's do a simple one. What if I said something like, hold on, let me erase this. I wanted something a little more complicated. But I'm going to go back to this one because I want to show you how this works in the truth table. So if we have a truth table for this, because this type of logic, the truth table is a little bit different. So we have P, we have Q, and we have P implies Q. Okay? Let's start with that. So I have true, 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 false, false, true, false, false. Now, for which of these does P imply Q? All but, which one?
Should there be a false?
Did I, oh, thank you. There we go. Which of these imply, or give us P implies Q? We did this last day. All but the second one. Because that's the one where the premise was true or the hypothesis was true, but the conclusion was false. So this is true, false, true, true. Now, I want to conclude Q. So I'm going to write Q again because I said it's often easier when you look at it side by side. Now, Q was what? True, false, true, false. How do I read this? Because we're going to be doing this in general, and I'm taking the easiest one, and we're going to make it more complicated. I read this by saying, how do I know if this is a valid conclusion? Okay, I look and say, which of these is the premise true on both? The premise is true on both here, and the premise is true on both where? See, my premise is that P implies Q and P are both happening. Where's that happening? Only here. Because here P happens, but P didn't imply Q. Here P implied Q, but P didn't happen. Does everybody see that? So the only place where that happened is this one. So this is the one that tells me this is correct. Is it possible to have more than one row that I can choose from? Yes. So that's why you always finish the table, because then you go back and say which rows. So what made this one a little bit different is I set up the truth table for this. That was easy enough. But now I'm saying P implies Q and P happened. Both of these have to be true premises before I look and see is the conclusion valid. And this one tells me it is right here. Because that was true and that was true. I'm not looking at that one, I'm looking at that was true and that was true, and then that was my conclusion. You with me on that? Because I want to do something a little more complicated now. I'm going to do, hold on, so where is it? I had it here. Oops. Oh, here it is, okay. We're going to do one that's a little bit busier than this. I would like it so anytime you had to construct a truth table, it's a sigh of relief for you. Not something where you freak out and go, oh my gosh, this is so hard. I mean, just true, false, you know, right conclusion. I would like to know the following. P implies Q or not R. Q implies P and R. Oops. P and R. Therefore, P implies R. Now, I'm not giving you actual statements. I'm saying P, Q, and R represent statements. The reason I don't want to give you exact statements, because then we start thinking about the statements themselves, whether they're true or false. Again, we said that's not relevant. Are my conclusions valid? So P implies this. I'm saying this is given. This is given. Therefore. So you could put an and here. You could say this is true and this is true simultaneously, therefore. But we tend to not put any symbols in between. So I have a truth table with a lot of columns. All right, so let's start with P, Q, R. I'm going to need a not R. Agreed? So what else am I going to need? I'm going to need a Q and not R. Or excuse me, Q or not R. I'm going to need a P and R. I'm going to need P implies Q or R. Or excuse me, Q or not R. And I'm going to need a Q implies P and R. And then the last column is going to be my conclusion there. P implies R. Whoops, P implies R. Try that again. Boy, that's a lot of things to fill out here. But once I do the first three columns, everything else should just kind of naturally fall into our lap. So how many rows? Anyone?
8.
And how do you conclude 8?
3 things.
So 2 to the third power, that's the easy way. Are our tables unique? There's a lot of people in this room. Are we all going to have exactly the same table? Sure, we all have the same conclusions, by the way.
Yes.
Yes, but are the tables themselves unique? No. It depends on the order you put the trues and falses. I want to make that really clear, because a lot of times you'll go and check your answer in the back of the book. Hopefully you all do that. You're making a truth table and it doesn't look like yours, because the order you chose to do your trues and falses was maybe different than what the author did, but it's still the same conclusion. You're going to have the same number of T's and F's in every column. You're just not going to have them in the same places necessarily. So I tend to do it the same way I do it in a stats class when I'm doing coin flips. It's easier for me to keep track. So I do it like this. I go true, 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 false. True, false, true, true, false, false. There. I got my first 4. Now, false, true, true, false, true, false, 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 true, and false, false, false. Hopefully you can all see that. Everything else should just now flow. only the last column is really going to require thought. Does everybody understand that? There's no thinking required. I'm just saying, does this lead to this? Or what is the next thing I'm going to do? Even before we get to the implications, these should be automatic. You really shouldn't have to think too hard. So now, not are, false, true, false, true, false, true, false, true. So, Q or not R. Let's make sure we look at the right columns. Q or not R. Well, actually, most of these are going to be true, aren't they? That's going to be a false, because it's an or. Q or not R, true, true, true. And then that's going to be a false, and then true. True, true, let's see, did I get that right? Q or not R. The only places where they're both false is here and here. Okay? It's a lot of truths. Now, P and R. P and R is not going to have a whole lot of truths, is it? Because it's an and. So I think I'm only going to be true here and here. Is that right? First and third rows? Sometimes it's easier to look for the, the one case. So the first and third rows, and then it's false everywhere else. Now, P implies Q or R. So I'm now looking at these columns. The easiest way for me, when I'm doing implications, I look for the falses, I don't look for the truths. And the only way an implication is false is if the hypothesis is true and the conclusion is false. Everybody remember that? That's the only time it's false. So do I have any cases where the hypothesis is true and the conclusion is false? It looks like here in the third, and then everything else is fine. It's only the third, isn't it? Because if the hypothesis is false, the statement can't be false. Remember, it's only if the hypothesis holds but the conclusion didn't happen. You scored higher than 90% in the class and you didn't get an A. Well, there's a problem with that. But if you didn't score over 90% of the class, it doesn't matter what the conclusion is. Because the conclusion says if this happens, the conclusion's guaranteed. If the premise doesn't happen, there's no problem. Again, the only case where it would be a problem would be, I believe, this one here. So in the third row, we get a false implication. And all the rest should be truths. Implications can be tricky because you have all these falses and go, wait a minute, how can it be true? I didn't score over 90% and I didn't get an A. There's no lie there. I didn't score over 90% and I did get an A because of all my extracurricular. Okay, that's not. I scored over 90% and I didn't get an A. That's the only one that would be a problem. Okay? Now, Q implies P and R. So now we're looking at here. Do I have any falses? I have a false in the second one. Where are we? Q implies, okay, so true, that's false. Now, all of these are fine, and now I get to the fifth row. I have a true false here, and the sixth row I have a true false. Ooh, I have a couple of falses then, don't I? So true, true, and what did I say, the fifth and sixth? Make sure I'm in the right place here. So these guys, the last three are true. And I think our falses are in the fifth and sixth. Again, let me just make sure. So true, false. That's a false, it's automatically true. That's a false, so it's automatically true. True, false, so that's false. True, false, so that's false again. And then true, true. So I think I have my falses off by one. There we go. Does that look right? I'm looking at this big picture here.
You have 9.
Yeah.
and
Oh,
that's it.
that's the problem. Okay. This is what I said, graph paper is a really good way to do this. Okay, so we're in the fourth row, and in the fourth row, we should be true. We had a false in the second. Now in the fifth row, we should be, Q implies, hold on, I'm looking at the wrong one, sorry. Fourth row is true, fifth row and sixth row are false. Oh, I did have that right before, I just did too many, didn't I? There we go. And then true, true. Is that okay? You guys help me out. You have a better view. Finally, now, can I say P implies R? Now, don't look here. The original problem said, we're going to assume that this statement is true. We're going to assume that this statement is true. If both of those statements are true, is the conclusion true? So the only place I actually have to look are in these two columns, and I'm looking for the places where both are true. Okay? Which places are those? Okay? Well, this are true in this case.
Yes.
In other words, I have true, true. Where does P imply R? Actually, let's just go to here. Where does P imply R? Everywhere but one, let's see, row 2 and row 4. Row 2 and row 4 are false. And everything else is true. P implies R as true, false, true, false, true, 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 true. So now, only places I'm looking are the places where both premises are true. How many places does that happen? Does that look right to you? There are 4 rows where both premises happened. Does it matter for example, does this one matter to us? Sorry, over here. This is true. If this is true and this is true, then we're saying this is the conclusion we're going to get. In this row here, the second one wasn't true, so it doesn't matter. They both have to be true. The implication is not this implies this. This is if both of these are true, then this happens. Both of these are true, it happened. Both of these are true, it happened. Both of these are true, it happened. But in this case, both of them were true, and it didn't happen. So, this is where the red light is flashing right now. The question was, is this a valid statement? And the nice thing is I don't actually need to have a P and a Q and an R. I don't actually have to have sentences. Is that a valid statement? Yes or no?
No.
No. We found the one case that didn't work, and that's all we need. So this is pretty powerful. This is pretty huge. But again, this is a logical statement. So it's often the case you have all of these different things going on at once, and you're going, can I make this conclusion? That's the tricky part. Can I make this conclusion? And in this case, this was easy. Because the premise was, in this case, P implies Q, and P both had to be true. And this was the only line where they're both true, so this is the only line that mattered, and the conclusion was true. That's what makes this a little bit trickier, is because I have to fill out a whole table and then figure out where I'm looking. Everybody got that? So let's try an example of this. I want everyone to try this on their own for a moment. You see, the benefit of a truth table is that there's no calculating, and I really don't have to do a lot of thinking. I just have to read it correctly and say, okay, you know, if this is true and this is true, is this next thing true? So let's try, we'll do problem number 9. Let me enlarge this. Where the heck is the plus sign? Oh, here we go. Look at number 9. This is pretty huge. All right. Go one more. Okay, can everyone see that pretty clearly? So I got a whole lot going on here. I have P and Q implies not R. P or not Q. Not Q implies P. We're saying all of these things are true. Okay? Actually, you know, before we do number 9, let's do number 6 first. Let's start with a small one. Let's start with the ones a little bit smaller. Let's do 6 first. So P implies Q, Q implies P, therefore P or Q. It doesn't matter if you believe the statement, it's can you produce your answer based on your truth table? And the truth table, we're saying, is factual. If I produce it correctly, I should be able to read it easily. So as a group, let's all try this one. Yes, I can do it for you, but I think you get more out of it if you start it yourself. So how many columns am I going to have here?
4. 5.
Q plus P. There will be a column for each of these, clearly. So I'm going to have a P, I'm going to have a Q, and I'm going to have an OR. I'm going to have a P implies Q, and I'm going to have a Q implies P. Do you all agree? It would probably be wise to do P followed by Q, and then go right to the implications. P implies Q, Q implies P, and then finally P or Q. If I do it in this order, then I think it's going to be easier to read the answer, and I don't have to reproduce anything. So, let's all try this. How many rows? Three?
5.
4, 2 squared, 4 rows. It's just, you're flipping 2 coins, quite literally. All right, I'll help you here. I'll help you get started. So true, 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 false, false, true, false, false. Now we want to fill in the rest of the table based on this. Now the implication parts should not be challenging, but you got to make sure you read them correctly because one of them is going in reverse. Remember, the only time an implication is false is if the first statement is true and the second statement is false. Every other situation, it's automatically true. That sometimes defies logic. We're like, how could that be? Again, if the condition happens, but the conclusion does not, that's the only time we have a problem. If the condition or the hypothesis does not happen, does not matter what the conclusion is. It's not a false statement. All right, so P implies Q. Are any of these false?
Just the second one.
The second one only. You all agree with that? Q implies P. Are any of those false? The third one, because now I'm going this direction. That's why I said it's a little bit trickier. So that would be the false here. P or Q. Are any of those false?
The last one.
The last one is false. That's it, because it's an or. P implies Q, Q implies P.
Why is the last one false?
Oh, because it's P or Q.
Oh, okay.
Yeah, because this is an or statement, so I'm just looking at these guys. If one of them is true, then the or is true. Now, are we done filling out the table? Yes. Was that hard? Hopefully not. Now the hard part. Where does the conclusion come from? It doesn't matter if you believe it or not, because we're not given actual statements, right? We're calling them P and Q. I had an orange pen. Where did that end up? Oh. I need the orange here. Where did I leave the orange one? Okay, well, I guess I'll have to use black then. Normally this calls for orange, as you all know. Yeah. So where am I looking? I'm looking where both premises are true, which would be here, not here, not here, here. So what do you think?
Not a conclusion.
Is this a valid conclusion? No. I'll give you a simple example. If we score more points, then we will win the game. If we win the game, then we scored more points. Therefore, we either won the game or we scored more points. Obviously, we didn't actually play today. Does that make sense? Oh, there was no game. We just said, what will happen if we score more points? We'll win. What can we say about a win? We scored more points, but we never actually played a game today. So therefore, neither one of, this is not P or Q. That doesn't imply that a game was played today or that we scored more points. We're just saying what would have happened. I'm trying to give you a really simple example of why this is a false conclusion. Oh, okay, because we didn't actually play. Okay, so the conclusion is this is invalid. That's the proper way of saying it. Because the question was, is it valid or is it invalid? Now let's go to one that's a little bit beefier, okay? I like the beefy ones. You know, let's do 8 instead, actually. Not as many columns. There's just so many columns in 9. We'll try 8 instead. 8 is pretty beefy, but it's not as beefy as 9. What about what happened to my orange pen? Okay. So problem 8 says P or Q. P implies not Q. P implies R. Therefore R. So what am I assuming? Because I'm trying to come up with something being valid or invalid. Am I making any assumptions here? Yes. I'm making the assumption that the first 3 statements are all true. That's how we read this. The first statements are all true. And therefore this conclusion is absolute. Now, question, is that valid or is that invalid? I don't know yet. I have to actually do it. You could try putting in statements. You could try doing mathematical problems. You could say, let me throw some inequalities numerically in there and see if this works. I think that's too hard. Because now you're looking for counter examples, and there might be, but it might be too difficult to find one in this context. So just simply making the table, in this case, is way simpler. So, how many columns? I'm going to put way up here. I have P, I have Q, I have R. What else?
Not Q.
I have not Q. Well, let's do P or Q first. They're right there. And then I have not Q.
P implies not Q.
P, oh boy. I might have to do it over there. I'm not sure I can fit all this in. We have P implies not Q.
And then P implies R.
And we have P implies R. And I guess we don't really need to write therefore R because this is where writing the R again, I'm a big fan of because you can read it easily. I just have a screen in the way. Maybe I'll do it at the end. Does everyone understand why you would choose to write the R as the last column? Because over there, that's what you're comparing. You don't have to. You just got to make sure you're reading the correct place. And when there's this many things, sometimes reading the correct place is not that easy. All right? I'll try to write a little bit smaller so you can fit everything in. All right. I wish I knew what happened to my orange pen. I could have sworn I. All right. So we have true, 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 false. And by the way, this is not a joke, but there's a lot of folks, this one is kind of funny, but it is kind of sad. We're all used to doing this. You remember back in elementary school, maybe junior high, you took that true-false test. And so on every one, you did one of these. You guys remember doing that? I've done this at the college level. I've asked true-false questions, and on every one, I get that symbol. It's the ambiguous, well, interpret it any way you want, Mr. Brown. Or, even better, that one. Well, that's just the way I make my F's. Then how do you make your T's? Don't make your symbols ambiguous because for the simple reason you're the one that has to read them. And if you're ambiguous, you will misread it. So I say it's jokingly, but people actually still do that at the college level. They'll write the symbols hoping, if they don't know the answer, they'll write an ambiguous symbol. So true, false, true, and then true, false, false. False, true, true, false, true, false, 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 true, false, false, false. All right, so the next stuff should be fairly simple. P or Q, the only ones P or Q, the only ones that are going to be false are the last two. Do you agree? So that makes it a little bit easier. So true, 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 false, false. Not Q, I don't have to think, I just read. So not Q is going to be false, false, true, true, false, false, true, true. Now, P implies not Q. Now we got to think a little bit. P implies not Q, and again, on implication, I think it's always easier to look for the falses. A false implication would be, again, if the hypothesis is true, the conclusion is false. So anywhere where P is true and not Q is false. Does that happen? Yeah, it happens on the first two, doesn't it? So those are both false. True, true, and then all of these are automatically true because the hypothesis didn't happen. So I have a bunch of trues in a row. Beautiful. Now finally, P implies R. Same thing, look for the falses. I think we're going to have a false in the second row and in the fourth row. Are you with me on that? And those are the only places? And then true, 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 true. Now I'm going to cheat. I'm going to go ahead and rewrite the R here because it'll be easier to read. Hopefully you can see this. True. This is alternating true, false, true, false, true, false, true, false. I'm going to do that because it's easier for me to read. Now, what had to happen? All three of these things had to be true simultaneously. We probably should have put the not Q first, but that's okay. So when are all three true? Not here, not here. Ah, here they are. Do you agree? True, true, true. Anywhere else? No. How about here? I think this is all three were true. Remember, I'm looking at this column, and this column. True, true, true. We just found our outlier. All right. Does that look correct to you? Those are the three places where all three premises were true. And in this case here, again, if I had to do over again, I probably would have put that one before that one. That's okay.
Is there any notation like suggested to mark out which one's your premise and which is your conclusion? Because it's easy to like get confused with the amount of tables. Do you see what I mean? Like at the top,
Well,
mark in some way that one's the premise.
when you're writing this obviously is the very, very last column.
Right.
And if I set this up well, now again, if I'm doing this on the computer, I'm using lots of space, so that's not an issue. If I'm doing this on paper, I'm going to write small enough to fit it all in. What you really would like is that these three columns are at the end and then followed by this one.
Okay.
I should have wrote those in reverse order. It would have been easier to read. But now I'm looking for three truths in a row and then saying, is this one true or false? And in these two cases, all the premises were true and the conclusion was true, but in this case, the three premises were true and the conclusion was false. So what is my final answer to this? Simply one word: invalid. Don't say false or whatever. You're saying, is the statement valid or invalid? Is the logical conclusion valid or is it invalid? You don't have to say why. Your why is apparent in your table.
So what we would do if we were to write like the sentence is we would write invalid and then box it underneath the premise, or like the logical statement.
I would just say, somewhere on here I'm going to say invalid. And I'm going to point out that one right there. That's it. You don't have to write an explanation. Your explanation is right there. I didn't get a true value there, so therefore it's invalid. That's it. You don't have to do anything else. But you do have to, I circle the rows. I always do that. When I'm doing this on a quiz key, I will make those rows bold so that they stand out. And you go, okay, yeah, these are the rows. Why? Because if I make my conclusion by looking at the other rows, then my conclusion is going to be incorrect. I might still get the right answer, but I'm getting it for the wrong reason. Has that ever happened in math? I used to teach remedial algebra, and I'd be teaching how to work with negative signs, particularly multiplication. So I would ask questions like -1 to the third times -2 times -1 times 1 times -1 to the fourth power times -1 times -2. Well, the answer is either going to be 4 or -4 because you only had a 2 times 2 ultimately. And how did they get the answer? By simply counting the number of negatives and determining if it's odd or even. We know this. But I would have people actually doing running totals along the way make a series of errors along the way and sometimes get the right answer. Why? Because they made exactly 4 errors. But the person who only made 3 errors got the wrong answer. So when we're working with negative signs, you're going to get the right answer accidentally half the time probably, because you just miscounted and the odd and even. And it sounds kind of funny, but that's true, right? We all know that, was it 2 wrongs don't make a right, but 3 lefts do? Think about that. Just because it ends up in the right answer doesn't make it a valid path. I took 3 left turns when I was supposed to turn right. I'm going to end up in the right place eventually. Think stop signs. So just because an answer, the final answer is correct, the path has to be. So everything I'm showing you literally is all you would need to show. There's no words involved. Where it gets tricky is if there are actual statements involved. Does that ever happen? Well, yeah, that's exactly what we're going to be doing in general. So I gave you an example with Tyrion, right? I gave you words instead of symbols. Sometimes that's easier, sometimes it's harder, because the errors that we make. Now I want to go backwards a little bit. This is pretty big stuff. This is pretty beefy. So now I'm going to go back to symbolic form. Okay? This is one of the most common. We're going to do 2. I don't want to take that up yet because I'm going to come back to it. It just takes too much time. I want to determine the validity of each of these. Do you think they're valid, both of them? George is very skeptical. You know, I didn't want to. But it's really the question is why? And it's really hard to make a verbal argument because it sounds good. All cheaters sit in the back. Larry sits in the back, therefore Larry's a cheater. It sounds valid, but it might not be true. How do I prove it's not true? Don't try to come up with cases. Simple truth table. And then I'm going to tell you the type of reasoning that we're going to be using because this is going to be a common answer that we give. So in this case here, I have a P, I have a Q, what else? I have a P implies Q, and then I'm going to restate the P at the end because, again, I want to compare the last 3 columns. You do not have to do that. But like we saw in the last problem, if my columns aren't all in a row, is that potentially difficult to interpret? Could we have made a mistake on that one? Because I had to look at columns that expanded. So, oops, sorry, starting here. You don't have to do this one, I just think it's easier if you do. P implies Q, oh, sorry. P implies Q, I'm going to restate both of them. Q and P again. All right, so true, 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 false, false, true, false, false. It's redundant, but I'm going to put them over here because then it's easier to read at the end. P implies Q, we know that's true, we know that's false, we know that's true, we know that's true. Now, do I have everything there? Oh, sorry, I got these backwards, sorry. That's true, that's false, that's true, that's false, and then that's true, true, false, false. Sorry, almost had that backwards. Now, I did not have to rewrite these, but it would have made it trickier. I would have been looking right to left. That's not incorrect, but it feels backwards. So I redundantly restated those last 2 columns. So what am I looking for? I'm looking for the cases where both of these are true. And that clearly happens here, and it clearly happens here. Therefore, Jordan, it's invalid. There's an actual name for this. P implies Q. Q happened. Therefore, P happens. Doesn't that mean that Q implies P? If Q happens and I'm saying therefore P has to happen, doesn't that mean Q implies P? Yeah. P implies Q and Q implies P. Q implies P is called the converse. This is an incorrect conclusion. This is an invalid statement. But why is it invalid? This is called a converse error. I gave you a conditional that we are assuming is true. Can you ever assume the converse is automatically true? No. This says if P, then Q. Q happened, therefore P happened. But that means that Q implies P. Q happening guarantees P happening. But that's not the case. Because this is true, it does not mean that it's true in reverse, and we see that right here. This is called the converse error. All cheaters sit in the back. Larry sits in the back, therefore Larry's a cheater. All cheaters sit in the back means if you cheat, then you sit in the back. Is it valid to say if you sit in the back, then you cheat? Is that valid? No, because that's the converse of the statement. Larry sits in the back, therefore Larry cheats is an incorrect or invalid conclusion because it's the converse of the statement. All cheaters sit in the back. Larry's a cheater. Therefore, Larry sits in the back. Is that a valid conclusion? Yes. P implies Q, P happened, therefore Q happens. That's the modus ponens. That's the absolute. This is not modus ponens because it's backward, and this one tricks us. This one gets us all the time.
Okay, so if we look at these statements and like, yeah, that sounds good. Make the table and like verify. But if we look at it, it's like that doesn't sound right because what if this? Can we just write? Well, in this case, it wouldn't work out.
Well, the problem is there's an infinite number of possibilities for the P's and Q's. So, there, by the way, are we going to look for counterexamples? Are we going to look for actual counterexamples? Yes, yes. But not in this case, because there's too many possibilities that if I'm looking for counterexamples, I might not be able to see a clear and obvious one. There will be counterexamples. There's an infinite number of times when this is probably false if I actually set up the situation. But that's too much. That's way too much of a burden. It's easier just to look at this, because what if this was a valid conclusion? And I'm trying to find counterexamples. All of you have done this before. How many have had Calc 3? Remember doing limits in Calc 3 when you first started limits? And you're trying to determine, if you can take that limit as x comma y approaches a point, and you might be able to find it algebraically, or you try that multiple path rule, let's approach on a different path. You guys remember doing those? Problem was, if the limit existed and you're spending all your time trying to prove the limit doesn't exist, it's a futile attempt. You won't be able to do it. So if the limit existed, you can't be trying to show it doesn't exist, you're trying to figure it out. But a lot of times you look at a problem, you don't know which way it's going. And because you don't spend a lot of time on those. But the Calc 3 limits are very, very tricky. Because sometimes the limit doesn't exist and you can prove it doesn't exist. But you have to have an actual plan. You have to first believe it doesn't exist. If it exists, if something is true, you can't prove it false. But if something is false, you can't prove it's true, and all you have to show is one instance where it's false. That's what the counterexample is. This is not the type of problem you want to do that with. I think it's way too much. This is easy right here because I see it. Now, the next one is very similar, but notice what I'm now giving you negations. So this is quite different. So, actually, let me use black. So I've got P, Q. Let's go with P implies Q. Then let's do not P, and let's do not Q. That makes it kind of easy. I don't have to restate anything, and then I only have to look at the last 3 columns, right? Everybody see this is probably the most efficient setup for this problem. All right, so we are true, 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 false, false, true, false, false. P implies Q. Walk me through it. True, false, true, true. I want this to feel automatic. Right? This, you do a few problems, you get the hang of it. Now, not P, that's easy. I just take the opposite of those. Not Q, I take the opposite of those. All right, what rows am I looking at? Am I looking at all the rows? I'm looking at the rows where these 2 statements are true, which would be that row and that row. Everybody see that? That's why I circled. Those are the only places where the answer can come from. And again, what do you see? So is it valid or invalid? But is it the same error? No. P implies Q. What do we know about negations? What's absolutely true? If P implies Q, then not. It's called the contrapositive. We did this yesterday.
Not P, allies.
P implies Q, not Q implies not P. If you score 90% or better, you will get an A. You did not get an A, therefore you did not score 90% or better. If we score more points, we will win the game. We did not win the game, therefore we did not score more points. It's absolute. If P implies Q, then not Q implies not P. That's called the contrapositive. They're absolute. They go, is that what this is? P implies Q, does that mean that not P implies not Q? No. Of the four terms, remember we had conditional, converse, inverse, contrapositive. Which is this?
Inverse.
This is the inverse, which is the contrapositive of the converse. Oh my gosh. So this is called an inverse error. And I'll remind you of the terminology because these are things we need to know. Whether you've seen them in a previous class or not, I don't care. You're seeing them in this class. And by the way, in any class that deals with logic, the definitions and the conclusions that I've been talking about when you're talking about things like contrapositives and stuff, it doesn't change meaning from one situation to the next. So I'll write it as in this form. Now, last time we used the double arrow. When you're actually doing things in a math class, and you're writing mathematical statements, if you ever look at my answer keys, some of you look at my answer keys, I'll have a statement, and you'll see the implication symbol, and I'll give you another statement. I'll say, the conclusion is valid based on the previous step. If 4x equals 8, then x equals 2. You know, I'll use an implication symbol often to say, hey, the previous thing now guarantees the next thing is true. In the logical connectives that we're doing now, we use a single arrow. It's the only part of this course that we do this. And it's confusing because we used the double arrow before. This means the exact same thing. It's just that this is the notation of choice. It wasn't there when they decided. Again, I would have said, let's leave it the other way. This is called the conditional. This is called the converse. Converse. This is called the, this is the inverse. And that's the contrapositive. And we did this last time, and I said, these two go together. If P happens, Q is guaranteed to happen. Q didn't happen, therefore P did not happen either. That's the contrapositive. They go hand in hand. If the conditional is true, then the contrapositive is true. Now, is the converse automatically true in general? No. Can the converse be true? Yeah, there's a lot of times. Remember we talked about that last day, biconditional. We use statements like if and only if. They go hand in hand. So the converse and the inverse are the ones that are not necessarily true, but these go hand in hand because the contrapositive of this statement is this statement. But in general, if I have a conditional statement, I know the contrapositive is true, but in general, is the inverse and the converse both true? No. All cheaters sit in the back. Larry doesn't cheat. Therefore,
Larry doesn't sit in the back.
is that a true conclusion? Larry doesn't cheat, therefore I think you can say Larry can sit anywhere he wants. All cheaters sit in the back. Larry doesn't sit in the back.
Therefore, Larry's not a cheater.
Therefore Larry's not a cheater. Is that a valid conclusion?
Yes.
Yes. And you see why switching them, you go, oh, I got to think about that. So if all cheaters sit in the back, if you say if cheat, then sit in back, not sit in the back, not cheat. Cheat, therefore, or cheat implies sit in the back. You sit in the back. That does not imply cheating. That's the converse. You see, they go, oh gosh, that's crazy. So when you're asking for counter examples, I don't think of these as counter examples. I just say, are we stating the converse or the inverse when we say something? Because the converse and the inverse, you cannot automatically say it's a true conclusion. So this was the converse error. We said P implies Q, but the very next thing really is saying Q therefore implies P. Here we said P implies Q, and this is now saying not P implies not Q. That's the inverse. And again, that's not automatically true. I know that if this was not Q, we could conclude not P. We started the class with that. Right? That's the contrapositive. Do you see why this is a little bit on the tricky side? So I'm giving you a simple truth table situation. These were a little bit more complicated. I'm giving you a simple truth table situation, and you come up with something that's not valid. Okay? First of all, there's 4 possible conclusions. Everything I said was a positive statement. P implies Q, and keep this real simple. Eraser. Because I want the conclusions to be automatic. When people say why, all right, let me change this one to, let me erase all this. We'll do this one at a time. P implies Q, P, therefore Q. We know this is true. This is called, it's true by what's called modus ponens. Modus ponens is the, by the way, I don't need you to ever say it's true by modus ponens, but that's actually the formal language. It is a true conditional, it's a correct conclusion. P implies Q, Q, therefore P. We just said that's not correct. If modus ponens is the conditional truth, we said this was not true because this is the converse error. I'm giving you all positive statements. Do you agree? They're all positive. Now let's do the negation statements. P implies Q, not Q, therefore not P. Is this true? I just used a contrapositive, didn't I? We didn't score more points, therefore, or excuse me, we didn't win the game, therefore we didn't score more points. This is true by modus tollens. That's what those terms mean. Oh, okay. If it's true because everything was a positive, I got a conditional statement, I technically use a contrapositive. This is true, and now not the conclusion, therefore not the premise or not the hypothesis. Got it? Now, what's the last possibility? P implies Q, not P, therefore not Q. All cheaters sit in the back. Larry doesn't cheat. Well, Larry doesn't necessarily have to sit in the back. But that says Larry must sit in the back. This is not true because it's the converse error.
Some of the inverse.
I'm sorry, thank you. Yes, good catch. Inverse error. So if it's they're all positives, it's modus ponens or it's converse. It's conditional or it's converse. Negations, it's contrapositive or inverse.
Modus is
Tollens.
Tollens.
T-O-L-L-E-N-S. Yeah,
Gotcha.
it's also in the textbook. You're going to run across those terms. I just want you to know, oh, that's modus ponens means I had a conditional. Modus tollens means I had a contrapositive. That's it. That's all I want you to interpret. Okay. I don't need you to tell me that that's the reason. So usually I'll just say, is the statement valid or invalid? If it's invalid, tell me why. Linear algebra. I give you a linear transformation. Is it 1-to-1? Is it onto? Is there an isomorphism? If it's not, tell me why. If it is, it is. I mean, it's kind of easy. But it's usually no because. Do you all agree with that? So invalid because. That's really how this works. It's valid. It's invalid because this type of error. This is a little bit more complicated. That's okay. We can all deal with that. Let's see. I think that is okay. Now let me move on. Now I'm just looking at the term. There's so much terminology. Now the next thing is going to be about language and stating things. I'm going to go ahead and turn this off for a moment. So we'd like to be able to state things mathematically and use the appropriate language, but symbolically. Learning how to write things symbolically, I can make things much more efficient. This is very efficient rather than me writing big statements, right? I would have paragraphs written if I was trying to do this with the actual words that each of these statements might represent. So, I won't finish the sentence. Dean Martin, right? Everybody loves somebody sometime. This is one of my favorite things to use in logic. Everybody loves somebody. We want to be able to state this using logical statements. Now, not an if-then. Everybody would be every person. What's a math symbol that we use for that? But what words? For all. Everybody would be for all people. Do you agree? Loves somebody. You love 3 people. You only love 1 person. But I'm sorry, everybody loves somebody. So therefore, everybody loves at least 1 person. You with me on this? I would like to be able to state this using logical terms. And that's why I love this sentence, because clearly there's a universal qualifier and there's an existential qualifier in this statement, 3 statements. So what we want to do is the logical. So we come up with something called a predicate. Don't worry about the language. By the way, if you guys are actually reading the text, which you should, it is a very well-written textbook and it is very easy to read. But there's a lot of vocab that's unfamiliar. So let's say P of X represents all people. X would be an individual person. P of X would be the whole thing. So we'd say the domain here would be all people. So for all X in P of X, that would be the set of all people. For all X in P of X, X would represent person. There exists not an X. How about let's pick a different variable? Or how about we can do it this way? For all X1 in P of X, there exists X2. Where does X2 come from? Also from the set of people, such that now we can use words or we can use symbolic notation. We can say X, we can use any symbol we want here. Well, you know, we can say X star Y means X loves Y. You can use whatever symbolic notation. You can make up a symbol. So if X star Y means X loves Y, then for all X1 in the set of people, there exists an X2 in the set of people such that what? X1 stars X2. Wow, that's crazy. But I'm introducing the mathematical notation that we will often use in this situation. Because we can also apply this to actual mathematical statements, algebraic statements. We can do things like that. Okay?
What's the symbol between P of X and X1?
Such that.
Such that.
Do you remember last day I introduced? So element,
Yeah.
if I write the element symbol backwards, that means such that. Gotcha. Does there exist limited to 1? No, it just means there's at least 1. That's it. And we're going to start getting used to this type of notation. Let's see. I want to start simple on this one. I want to do some real simple, hold on. Some real simple statements, and I want to use words first of all. Yeah.
What is that symbol between
I-
X1 and X2?
I just said I'm going to define a symbol. I'll call it the asterisk. X asterisk Y means X loves Y. I'm defining the relationship.
Okay.
You could use words. I want, in this context, do you notice I just said this without using a single word? Now, that's kind of cool. What do we want to be able to do? Translate statements to symbols and, just as importantly, translate symbols into words. Because I can give you a symbolic thing that's just beautiful and you go, but I don't know what that one symbol means. Then can you translate this? No. So that's why you need to be able to do both. If you were writing a math paper, something really, you know, high end, you're doing some major proof, you're going to use words, you're going to use sentences, but you're going to use a lot of symbolic notation. Okay? If you're doing algebra, I have fun with this. But at my house, you know, we always have, you know, if I'm texting my wife, I'll say things, you know, I will do things like this. You know, I'll write that out. You know, I was just the other kid. Have you ever seen Megamind? That's like one of the funniest movies ever. It's an adult movie. And he's typing LOL, smiley face. That's, you know, how the evil overlord. So I would type that when I'm texting my wife, you know, just for fun. Well, nobody writes you know, you don't write that. you write x plus 3. Nobody has issues with that. Nobody spells out the symbols as words, I hope. Right? None of you, when you're doing your calculus, spelling integral symbol, you're writing out words. No, you write the symbols because there's no ambiguity. But when you're doing something, you might explain, you might throw in some words as well. In linear algebra, you're writing a proof. You have a lot of symbols, but you got to use some words to say, here's how the thing is connected. Here's why I can say this. So in math in general, we're very used to using symbols. But can we write everything symbolically? Maybe. Do we have to write everything symbolically? No. Could I have said x1 loves x2 in words? Sure. That wouldn't have hurt anything. We were just having some fun. We wanted to write the whole thing. Okay. Every student in class loves, let's say, pizza. Can you write this using any form of symbolic notation? Is there anywhere you could write this as symbolic? By the way, do you have to write every single word symbolically? No. Every student in class loves pizza. Okay, let's call you X. Start it for me.
U of X is the domain. Oh, sorry.
How about just take, we don't have to, but if you're X, for all X,
Yeah. Within.
you could say element of
The class.
class, or you could say X in class. In that case, it really doesn't matter. For all X in class. Now, you love pizza. Is there anyone here who doesn't love pizza? I don't want to offend you. Okay. Do you love all pizzas? You put an anchovy on a pizza, I'm running. You know. Do all people who love pizza love all pizzas? Oh, I think not. Are there things you don't want on your pizza? Yeah, I don't like onions on my pizza either. Mushrooms. The magic pizzas. Sausage, pepperoni, black olive, and green bell pepper. I'm in heaven at that point. But you start throwing mushrooms and onions and stuff. Anchovies. Do you love? No. But you love at least one. For all X in class, there exists a pizza. You can just say a pizza that X loves. Now, I could go way more symbolic than this. We could define the set of people, you know, using symbols and all that. But I want to just throw in, where can I throw in a universal and or existential qualifier in a mathematical statement? Because those are really important. What if not everybody in this class loves pizza? Can I say for all? No. Can I say there exists? There exist students who love pizza. If I don't have everything, if I have something that's true a lot of the time, but it's not always true. The universal error we often make, and by the way, this is a major premise of next day's lecture. I have something that's not always true. There's one person here. It's Matthew. He's just not speaking. He just hates pizza. He just doesn't. It has to do with the circular shape, not what's on there. You know, he doesn't like pizza. Okay, so if I say all students like pizza, Matt says I don't like pizza. Okay, all students hate pizza. The problem we often have, and this is again a major part of next day's lecture, is when we're trying to come up with a universal qualifier and it ends up not being always true, we sometimes make the conclusion, therefore it's always false. And that's very incorrect. No, because it might only be false one time. Think of something like closure. I like to use this example going back to set notation. Does everyone remember what closure refers to? The term closure means if I take two elements of a set and I combine them using whatever operation you want to combine, usually it's addition or multiplication. But if I take two elements of a set and I combine them, if the result is still in the set, then we say the set is closed relative to that operation. So if I take vectors in 3 dimensions and I add them, am I going to get another vector in 3 dimensions? Yeah, I can't fail that. If I take two integers and add them, am I going to get another integer? Yeah. If I take two irrationals and I add them, am I going to get another irrational? Yeah, root 2 times, or excuse me, plus pi. Of course, if I add two irrational numbers together, I will, oh, wait a minute. What's the result of this? 0 and 0 is rational. Of the infinitely many cases where you can add irrational numbers and get another irrational, is it possible to add two irrationals and get a rational number? Yes. So we'd say the set of irrationals is not closed to addition. That does not mean that every time you add two irrationals, you get a rational. No, this is a counterexample. So when we're talking for alls, we like for alls. But if it's not a for all, it doesn't mean it always fails. It just means I can't use for all. Now, are there irrationals that when I add them will produce an irrational? Oh yes, infinitely many. So it'd be easy to say there exists. Sometimes mathematically what we'll do, if I want it to be a for all, but there is an exception. Okay? Now I want to make sure we understand this because I want to say for all if I can. Remember we called them IR, irrationals, the other day. True or false? Again, I want to use notation as much as I can to get you used to it. So now you're going to start texting in symbolic notation now, right? What does that say? For any two irrational numbers, x and y are just two numbers, so any two irrational numbers, by the way, by saying for all, I'm saying for every pair of irrational numbers, such that they're not the negatives of each other, then if I add them together, will I get another irrational? Absolutely. The only time you can add irrationals and not get an irrational is when they add the 0, which means they're additive inverses, opposite signs. That's it. Now, there's an infinite number of irrationals, and every one of them has an opposite sign, so it's going to fail an infinite number of times. But it's going to succeed far more. I hate to tell you this, we'll talk about this much later, there are levels of infinity. There are different types of infinities. The counting numbers, 1, 2, 3, 4, 5, you can number them. So we call that a countable infinity, because you can actually number them. It turns out there's a very clever algorithm, you can actually number the rational numbers. You can actually say this is the first one, this is the second one, this is the third one, and so on. There's an infinite number. But you can't number the irrationals. So there's an uncountable infinity. In fact, between any two rational numbers, no matter how small the interval, there's an infinite number of irrationals, and there are more irrationals in that small interval than there are rational numbers altogether. That's crazy math. Don't worry about that one, your head will hurt later. But there are levels of infinity. So as long as these are not opposite signs, my result will be in the irrational numbers. But this does fail an infinite number of times, but it passes, infinity squared if you want to think of it that way.
So for all x, y that are irrational, and x is not
They're not additive inverses, in other words.
What if x is the square root of 2 and y is 1 minus the square root of 2? And when you added them, you got 1.
Oh, there's a good one. Okay, so the question was, I said, is this true or false? You just found counterexample. The reason I put this on there is I wanted to take this out of it. So I love it. That's your new nickname. You're Mr. Counterexample. That's beautiful. If I say something and you're going, well, that sounds good, but is it always true? You found a counterexample. So I wrote a mathematical statement. I said, is this true? That was my question. Is this true? Well, if I throw out the additive inverses, and I get it. I said it fails an infinite number of times. So you said, let me take the additive inverse and just throw some other number on there. That's an easy way to show it. Okay? Now, finding a counterexample when it's numerical is often a lot easier. Okay? So let's continue with this type of thought. Okay? Because before when I said we're saying P, Q, and R, and we're trying to come up with the proper conclusions. You know, if P happens, then Q happens. And you go, okay, in other words, if you can fly, then you can disappear. Okay, I'm making this statement. This is not important if it's true or false. I'm making the statement. This is now absolute truth. If you can fly, then you are invisible. Now, with that, let's say, can I make these conclusions? But the first statement was ridiculous. No, it doesn't matter. If that is true, then what conclusions can we make? You see what my point is? If that is true. But now when we throw numerical statements in there, I can't give you a false numerical statement, or can I? True or false? This is actually true. Because if I add 1 to both sides, now 0 can't equal 1. Therefore, the premise was an impossible premise. But if I accept the premise, is the conclusion correct? It's crazy. I have seen a formal mathematical proof. I cannot remember what it looked like. I'm sorry. But the harmonic series, you guys remember the harmonic series in Calc 2, right? The sum of 1 over n. So 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6. It's a fairly simple proof, and actually there's multiple proofs to show that that is infinite. It diverges. It diverges very slowly, but it diverges. I've seen a mathematical proof that says if we make the following assumption, then you can show that this converges. I think it's actually a negative number. Have you seen the proof, Matthew?
Negative 112.
Yeah, I can't remember. It's a beautiful proof, but we know it's infinite. But if we make a certain assumption, then the conclusion is absolutely valid. And that's one of the confusions in a class like this. We're saying, no, if I make this assumption, what conclusion is valid? If the assumption itself is absurd, then didn't it really matter in the long run? No, we're just testing our logical skills. If this, then this is valid from a logic standpoint. It's impossible from an algebra standpoint. You with me? So I'm never going to ask you to prove something that's impossible algebraically. I just said, is this a valid conclusion based on this premise? The answer is yes. Now, that's kind of crazy. True or false? Now I'm saying, is it true or false? So now, what are you looking for? By the way, to prove this is true, if I said algebraically I want to prove this is true, that's difficult, isn't it? It is difficult in general to prove a true statement is true. Ooh. And we're going to do this kind of thing later on. I want to prove something is true, and there are an infinite number of cases. You can't show all the cases. So what you often do, and again, this is a major form of proof we're going to do later, you start by assuming your conclusion is false, and then show it leads to a contradiction. That's called a proof by contradiction. And that's actually a very, very powerful proof. A lot of the things you did in geometry involved contradiction, strangely enough. Okay? And because of that, some things are very easy to prove, but you actually start by assuming. So I'd say, well, if for all x and r, this is true. So if I thought this was false, I'm going to look for a counterexample. If I saw it was true, I might start by assuming this is not true, the opposite of this, and then show it leads to a conclusion. That's later. Is this true, or can you think of a counterexample? 3 squared, 4 squared, 1 squared, heck, 0 squared. In fact, if I take any negative number and I square it, absolutely that's going to be bigger than the original. Do you agree? So this is always true, isn't it? Interval notation. X is a real number between, this means this. What happens when you square a number that's smaller than 1?
Small.
It gets smaller, not bigger. Take a half. Ooh, so is this statement true? It is always true except here. In a mathematical situation, I want to use that to my advantage. I want to use this to prove some powerful theorem, say. But you just found a counterexample. In fact, how many counterexamples did I just come up with? Infinitely many, but it's a really small interval. So what if I said, for all x in R, excluding this, that I can say it that way. I can figure out a way of saying that. Now,
That's true.
what am I now saying in words?
For every integer.
For every integer, by the way, does it matter if it's negative? No, in fact, it's easier if it's negative. Because the square of anything is going to be bigger than a negative number automatically. Is this now a true statement? Always. Is it always true? Yes, it is actually always true. Because what did I just remove? I removed the only time it could ever be false because there's no integers between 0 and 1. So our goal is not to take things that are not true and then manipulate them. I'm just showing you that's always a possibility, the 0, 1 thing. If 0 equals 1, then, well, but 0 doesn't equal 1, so why would we waste our time? And that really is important. But in general, can I say something like this? Can I always do this? Yeah, okay, so what I want to do is now, a couple more problems. Because there's certain terminology. It's the for all and there exists that I want us to get used to. Yeah, okay, give me 1 second here. So it takes me a little while. When I scroll, it turns out I always miss too much. This takes a while. All right, give me one moment here. Can make the screen a little bit smaller. Okay, here we go. Oops. Sorry, this section's so long. There we go. Let me do the homework here. Okay, I want to start with the counterexamples because often those are the easiest to come up with. Okay, can everyone see this clearly? All right, I want to start simple. Okay, let's start with number 9. Now, what makes this really easy? The instruction says find a counterexample. Therefore, what can you assume about the statement?
It's false.
It's false. Because later, what is it? Determine if it's true or find a counterexample. That's way harder because it might be true. So I want to start with the easiest one. I'm telling you it's false. But so let's suppose I didn't tell you it's false. I say, is this statement true or false? And you'd say, it sure looks good. A number's always bigger than its reciprocal.
If it's bigger than
1/3.
What if x is smaller than 1? What if x is between 0 and 1 again?
Same thing.
It would fail, wouldn't it? The reciprocal of a small number is a big number. How about negatives? The reciprocal of a big negative number is a smaller negative number. So that would fail often. When is that statement true? Oh my goodness. Well, it's certainly true for any value bigger than 1. Do you agree? It's actually false the rest of the time. By the way, I said x in R. What about 0? It's kind of a problem, isn't it? So can you find a counterexample? What'd you say? You said 1/3?
Yeah.
Good, you're done. It is not critical or even always necessary to find all cases when something is false. Now, if it falls into your lap, and like earlier I did when I said the interval from 0 to 1, hopefully everybody was thinking about things like, well, a half will fail, right? When I square a half, I get a fourth. I just said, hey, it's always going to fail in this interval. That's not what you have to do in this scenario. You just have to come up with something that makes it fail. The good mathematician will say, wonder where else it will fail. Because I would like to actually make a statement like this, but then I need to put the qualifiers on for what intervals is it true. Is that statement ever true? Yeah, it is true. But when? Only for numbers bigger than 1. So I need to say that. So how could I change that to make it true? Could you say for all x in the interval 1 to infinity? Would that also be correct? Is that the same statement?
Yes.
Yeah. What's easier to read and interpret? Doesn't matter. Probably the first one. Now I can make it true. Okay? Let's look at the number 12. I have particularly fondness for number 12 because I just gave a Calc 3 final, and I had 3 different students on the Calc 3 final when they were doing the surface area. They had 16x squared plus 1, and that of course equals 4x plus 1. It's on my Calc 3 final. I actually had that happen multiple times. Is that true mathematically? Because that's what that statement's saying right there. Is the square root of a sum equal to the sum of the square roots? That's a tricky one. Even calculus people. Oops, sorry. Is that statement true? No, there's a middle term. It's called a perfect square trinomial. Do we all sometimes make goofy errors like that? If that statement was true, if this was true, then is this true? Yes. Because this says the square of a sum is the sum of the squares. That would mean the square root of a sum is the sum of the square roots for the exact same reason. Ooh. Now, how hard are you going to have to work to come up with an example? Because I can come up with an infinite number of cases where that is true. Let x be any real number and let y be 0. Oh, so how about let x be any real number and let y be 1? Now will it fail? Keep it simple, you know. Think Pythagorean triple. Okay, x is 16 and y is 9. Then the square root of 16 plus 9 is 5, but that's not equal to the square root of 16 plus the square root of 9. That one is easy, but this is the type of mistake we actually do. Even people at this level will make those kind of mistakes occasionally, but the people that make those mistakes actually make them regularly because there's a disconnect somewhere. But that's kind of silly, all right? But that's one. Now, I want to go to the next part because now we want to write things. Just have some fun. Consider the following statement. For all basketball players X is tall. Does it matter if that is true? You're not finding a counterexample for that statement. That's not the point. I remember my oldest son played basketball, was really good. Was thinking about playing at Mesa, decided not to. He's going to med school now. Or getting ready to go to med school. But he was an athlete. He played volleyball. And the one that he didn't realize, he goes, my God, everybody's so tall. He was just like playing basketball, all these volleyball players. And then one day I went to one of his games, and then one of the most important players on the other team was like, he was tall. There's a name, I can't remember.
Libero.
Libero.
Libero. I was gonna say the bolero, but yeah, not all volleyball players are tall. So if we start with, we're just saying, I'm making this statement. I'm not asking if the statement is true. I'm just saying, Jordan can turn invisible. Now let's look at what are the conclusions and what are the things that we can say based on that statement. Again, you guys see what I'm getting at? Don't try to determine if that's true, try to determine what else. Which of the following is basically saying the same thing? Because nobody here speaks with symbols. You speak with words, but you write the math symbolically, and we want to do the translation. So, for all basketball players, X is tall. All right. A, does that mean every basketball player is tall? Is A true? Based on that first statement. Is that an absolute? Yes. Second statement. Among all basketball players, some are tall. Is that a false statement? Does that say any are short? No. I've got a whole group of basketball players and I grabbed a few of them there. They were all tall. I didn't even look at all of them. It's actually a true statement. Because I didn't say any were not tall. That's more like there exist tall players. Does that make sense? So that's not a false statement. It's kind of an incomplete statement. Some of all the tall people are basketball players. If I start with every basketball player is tall, now let's go to the general population. There are a lot of tall people. Are all of them basketball players? Not necessarily. What does this say?
Basketball players.
Can I interpret that as there exist tall people that are basketball players? Yeah.
Only if there are basketball players.
But for all basketball players, XX is tall. Let's assume it's a non-empty set, okay? Because otherwise, there would be no basketball players. Now, the fourth line. Anyone who's tall is a basketball player. What is wrong with that? I'm looking for one word. Starts with a C.
Inverse.
That is the converse. What does the first thing say? For all basketball players, XX is tall. Can I interpret that as if you play basketball, then you are tall? Is that a correct interpretation of that statement? Yes. All basketball players are tall. If you play basketball, you are tall. What does 4 say? If you are tall, you play basketball. That is the converse. Ooh, that's why it's so important that we interpret the wording correctly. Number 5, all people who are basketball players are tall. Yeah, that's redundant. That's just rearranging the same words. Anyone who is a basketball player is a tall person. Yeah, we're not saying anything differently. Why am I pointing out examples like that? Because everybody here can have a correct conclusion, but use different wording to say it. And we want to be able to know, are the words we're choosing exactly the same thing? And that's why I throw out number 4. Because that's an easy mistake to make, isn't it? Converse error, all over the place. All right, give me a moment here. All right, now we go back to this one. All right. Number 14 is the same sort of thing. But now I'm giving you a mathematical statement. Is that a true statement, by the way? Is the statement itself true? When it is, it always makes it a little bit easier. Some of you are nodding, some of you are shaking your head.
It is true.
It is.
Is there a real number such that x squared is 2? Yeah, how many? Plus or minus root 2. So is it a true statement? Yeah. Did it have to be a true statement for me to analyze it? No, but if it's not a true statement, it does make it tricky, right? Are all basketball players tall? I don't know. And, but we're saying if we start with that assumption. All right, so. A, true or false?
False.
B,
False.
some real numbers have a square of 2. Wait, didn't you tell me plus or minus root 2? So some would mean there's at least one. So, by the way, some usually implies what?
1.
Probably more than one. If you only meant one, you probably wouldn't say some. I'm having a group over. Well, that probably means more than one person, right?
So are we trying to pick all the all the sentences that are true or all of them?
We're trying to identify if it's true or false. We just want to say, is that true or false based on the original premise?
And is that what equivalent means, as long as it's
Yes.
true?
Um,
Say that it's equivalent.
Let's use simple English, okay? If you score greater than or equal to 90% of all the points possible in this course, you will get an A. Can you say that differently? You could give me the number of points required to get an A. If my average in the class is above 90%, there's words you could use that say exactly the same thing as what I just said. Maybe you use fewer words, but we would all interpret it exactly the same way. That's what we're saying. We've been using this all class. There are ways you can say something that's different than somebody else, but you're saying the exact same thing, just the order of the words you chose, as long as you're not making it a converse or things like that. You see, we're not saying for all real numbers that's true. We're not saying that all numbers when they're squared equal 2. We're just saying there exists a couple of numbers out there that when we square them is 2. And now we're saying which of these sentences say the exact same thing using different choices of the order of words. Because that's important. Everybody here, when you are correct, you will choose your own way of explaining it that makes sense to you. We do this in everything, don't we? But does it mean you chose the same words in the same order as somebody else? Because the way you explain it isn't unique. So when we look at the statement, A says the square of each real number is 2. We know that's false. The second statement says some real numbers have a square of 2. Yeah. That's exactly what the original thing says, but it's completely different wording and there's no symbols. So that's the point. So let's keep going.
I have a question.
Yeah, Matthew.
So if we didn't evaluate the first statement and realize that there was more than one X, would the wording of B be false?
That's a tricky one. Because when you use the word some, does it necessarily, a lot of times in English when we use the word some we mean more than one. Somebody is going to go get me a donut today.
Isn't that right?
And that means exactly one of you, doesn't it? Oh, so in other words, it's a context thing. I would avoid using the word some personally. If it really was possible that it was only one, I'd say there's at least one or there exists. Because again, loose English, most of the time when we say some, but when we say something, that always means one. Right, you go into a restaurant, there's got to be something on the menu you like.
But the numbers also has a plural there, so I think B definitely implies that there's multiple, whereas the original statement only guarantees one. So that's.
No, the original statement says there's at least one.
Yes.
And it turns out there are. Remember, there exists means there's at least one. It doesn't mean there's exactly one.
But it doesn't guarantee 2.
No, it does. No, but the statement, there are real numbers out there. There's at least one real number such that that's true, and we know that there's exactly 2.
B guarantees 2, so it's not the same exact statement, I think is what he's saying. Because B guarantees 2 because it's using plural, so it's not the same exact statement as the original, because the original does not guarantee 2.
The original
guarantees
says
at
there
least
are
one, yeah.
Yeah,
but
there's at least one.
B guarantees
Right.
at least 2. So
And I
it's
guess
different.
it comes back to there's exactly 2 from looking at the problem. So yeah, you got that. What if I gave you a very ambiguous statement? Let's suppose I gave you a complicated. I'm gonna make this real easy. Hopefully, real easy. Okay. By the way, is this a true statement mathematically? I'm giving you a cubic. Yeah, a cubic has to cross x-axis. How many times can it cross x-axis? At most
Maximum
3. But this might only cross once. It might cross twice. I don't know. I would actually have to figure that out. Does everybody understand what I'm getting at? I really don't know. I could use Desmos, I could graph it. I do know this is going to cross at least once. Now if I throw in the statement some, I'm guaranteeing you there's more than one. What if this only crossed once, or I actually don't know? Then some would be an incorrect interpretation. The difference is we know that there's exactly two. That's why the sum is okay if I know there's exactly two, because the statement was so simple. But I like your thinking. If I didn't know there were exactly two solutions, then sum would be an inappropriate word, because sum is now guaranteeing more than one in this context. Again, not because I use the word sum, because numbers was plural. Okay?
Yeah, because in E, it does some real number has squared too. So it's literally the same statement, but S is different, and then you change up the letters.
Yeah, in that case, some real number is definitely singular. Because the number, so is E true? Yeah. Yeah, there's a real number out there. How about, let's go back to D. If X is a real number, then X squared equals 2. Ooh, is D true or false? No one wants to go out on here.
False.
It's false, because what does that say?
All of them.
That's basically saying every real number. If X is real, that's really saying all real numbers. Do you agree? What that is doing is that's changing the there exists into a for all. Ooh, so that one's not true. All right, how about F? There's at least one real number whose square is 2. What does there exist literally translate as? There's at least one. So F is probably the most literal translation, isn't it? There is at least one. It's not saying there's two, it just says there's at least one. So again, we can all say the same thing, but our language sometimes, we don't want it to vary too much.
So B is incorrect, but E is correct. Just to confirm, like.
Again, it goes back to the beginning. Because the statement was so simple and we knew there were exactly two, but the there exists does not imply plural. So that one's a little bit ambiguous. I'll leave it at that one. Do we agree that that is ambiguous? That's why I used the last example. Does anybody know how many solutions that has off the top of your head? You can all factor cubics easily, right? Problem is it probably has 3 irrational solutions. No, worse. It has 1 irrational solution and potentially 2 complex solutions. In other words, if it only crosses once, that means it has 2 complex, because that has to have 3 solutions. Yikes, I don't want to figure that out, so that's why we'll stop with there exists. I'm guaranteeing there's at least one. I'm not even claiming there is a second or third without knowing. Now, what if I knew the answer? I knew all the roots, and I knew there was more than one. Well, the there exists doesn't change anything, but if I knew there was more than one, then I'd say there are some values, because I knew there was more than one. So in that context, if I know there's more than one, saying some is okay, and there's nothing wrong with the original statement, but again, there's an ambiguity created when I use the word some as opposed to there exists. Because in that context, I think in the context of number 2, we all agree that some implies plural, whereas in number, or in E, that means singular. So I think E, if you were saying it in words, E is a better statement, right? Because I'm saying, hey, there is one. I'm not saying there's only one. I'm not limiting it to one, okay? So this section is a lot about language. Tomorrow we're going to do one of the more important things when it comes to the big picture, and that's how negations fit in. Because everybody loves somebody. I'm going to say, well, what's the negation of that? Nobody loves anybody? Think about a statement like that. How do I write a negation? How do you write a negation for all where there exists? That is an incredibly important and powerful thing mathematically. Again, some people get caught up and they miss the point, and they'll say, well, it's not always true, therefore it's always not true. Is that valid? If something's not always true, then it's always not true? No. Use the sum of irrationals being irrational. That's not always true. It doesn't mean it's always not true. It's usually true. It's just not always true. And when we do negations, we often make an incorrect conclusion because we're not sure how to treat absolutes. When you make a negation of an absolute statement, that's tricky. If I just ask you, okay, there's somebody here who made $1 billion last year. I'm saying there's at least one person that made $1 billion last year. I haven't even told you the formula. How would you negate that statement?
There is not
For all.
Just in words. Somebody in this class made $1 billion last year.
No one in this class made it.
No one in this class made good. Nobody made $1 billion last year. How many have had statistics? We're gonna do a little of the mathematics. I love the mathematics of at least one. Because what's the complement of at least one? None. I'm throwing darts at the dartboard. I'm throwing the dart n times. How many bullseyes potentially are possible? N. So you're going to bet money that I'm going to make at least one, and you're going to bet money on the complement, which is I made none. So when we do this, and I'm going to do some of the statistical examples next day because there's mathematical examples. I love things like this. You know, Matthew's an 80% free throw shooter. So if he goes to the line 10 times, what's the probability? Oh my God, that's a combination. That is such a complicated thing. No, what's the probability that he makes at least one? That's really complicated because I have to calculate the probability of 1 or 2 or 3 or 4 or 5 and add them all up. Or I can calculate the probability that he misses every one of them, which would be 0.2 to the end, and then subtract that from 1, which actually from beginning to end will take me about 8 seconds on a calculator. The mathematics of at least 1 is very friendly. The mathematics of exactly 1 or 2 or 3 or 4 is very complicated. We're going to actually look at that like the third to last lecture of the semester, section 9.5. That's complicated and you need a calculator. But the mathematics of at least 1 is easy because the complement of at least 1 is none. So we're going to talk about that from a formal logic standpoint tomorrow because we want to be able to do negations of absolute statements or even there exists. There's at least one billionaire in here. What's the negation of that? There aren't any billionaires in here. That makes it really easy. Everybody here last year grew 3 inches. I didn't say which direction, by the way. Maybe it was sideways. How do I negate that? Just think simple. Nobody did? At least one person did. Yeah, it's actually that simple when we start getting into it. All right, can you go ahead and hit the record? I'm going to stop. And hopefully today we didn't.